Okay, so as we look at module 6 here, we're going to be looking at vibrations. This is going to be an introduction to vibrations, and we are going to be looking at the very beginning, just the first section in chapter 19. So as we look here, this is our PowerPoint presentation, and we've got some things to talk about. So at the beginning here, we're just going to do an introduction here to the fundamentals of vibration. Now, mechanical vibrations result when a system is displaced from its position of equilibrium. Now, that equilibrium can either be static or dynamic, okay? So we can have, when we have static equilibrium, as we know, all of the forces equal zero, and we are at rest. Dynamic equilibrium just tells us that we are moving. So for instance, a state of dynamic equilibrium would be when we have, for instance, a constant velocity, okay, where we're not speeding up, we're not slowing down, and we're just going in a straight line. That is in dynamic equilibrium. So if we're looking at vibrations, it just means that we're no longer at an equilibrium state, okay? So if a force then knocks it, if you would, out of equilibrium, typically what vibrations are is that want to get back to equilibrium and trying to do that. So as the force subsides, the system tries to move back towards that equilibrium state by restorative forces such as maybe gravity or by the system's or material's inherent stiffness, okay, or springiness, if you would. The system develops velocity, so it starts moving around, which at first may not reduce to zero. So then it kind of floats up and down or back and forth, whichever direction it's in, trying to find that position of equilibrium. If the system overshoots the initial equilibrium point, then that velocity slows and switches direction and goes back again to try to get to it. So that process repeats, for that system until it regains equilibrium. Okay, so vibrations many times are not desirable. Okay, so a lot of times when we start to feel vibrations, we know that there's a problem. Like even when you're in your car, if you start to feel something that's not smooth, you're kind of like, wait, what is that? So it's usually a disruption of some point and usually not desired. And if vibrations are excessive or that they occur for long periods of times, they can compromise materials. So it's really important to have a handle on it. And that's what this introduction is about. First of all, really just defining it and getting you familiar with, what's going on with vibrations. So we're going to look at the next slide here. And this is a nice kind of before and after. So on the left-hand side, we're going to notice that we have a spring that right now is unstretched. So there isn't anything suspended from it. Then what happens is we add a block here. And what that block does with its weight is it extends that spring to a distance. It deforms that spring, if you would, and it elongates it. And now at this position right here, you're going to notice that it says equilibrium. So right now it's in a steady state where the weight of that block going down is equal to the tension in that spring or the force in that spring holding it up. It's not moving, okay? It's at an equilibrium state. Now, from its unstretched to its stretched, this would be what we would call the deformation, like in that spring or in the stretched state. The assumption here is that it is within the elastic limit of that spring. And we talked about that a little bit, maybe one or two times ago. And as we know that what that means is if we would take the load off of this, the spring would go back to its original shape and none of its mechanical properties have been compromised. If it's outside of that elastic limit, it means that some permanent deformation has occurred. And then we can't make predictions about the behavior of the spring. But the assumption here is we are in that elastic limit when we're at the equilibrium state. Now, over on the right, what happens here is that the spring now is being pulled on beyond that equilibrium state. So if equilibrium is here, we've now pulled down on that spring or on that block. And what has happened is block still has that weight, but now there's a larger force as the tension in the spring is now, being extended. Now, you'll notice that this is an x distance right here. I'm not crazy about the fact that they call it an x distance, but in the equations, they use the variable x for distance, okay? It is a vertical movement. I wish they would use y here, but again, it's really just depicting distance as opposed to which direction it's in. You'll notice here that there is an x sub m. Okay, now if we started that equilibrium point of 0, again, that's kind of our base, if you would. The maximum distance that we can stretch this down, or that is, you know, I guess the place that the maximum place where this application would go, this is going to be called the max x distance, or the max distance that we would intend this to go. And then you're going to notice that we also see it on top here, okay, as a positive and a negative. So again, that's the same distance down as it would be up. And that's the maximum distance we would see this, okay? That's going to come in handy a little bit later. Okay. So in this state right here, anywhere from below 0 down to the xm, this is now going to be in an unsteady state that this spring is going to want to oscillate, trying to get back to that equilibrium state. And as it said in the description, we might pull down on this and it's going to try to go back to equilibrium, but then it probably will spring up and go back and forth until it ends up getting back. So the worst case scenario is going to be where we're at these maximum x values, and then it gradually goes back to its equilibrium state, as long as there's not additional forces continuing to cause that to be out of, if you would, balance. Okay. Now, the way that this behaves is going to be very similar to what we call simple harmonic motion. We've seen simple harmonic motion before. Does anybody remember where? I'll watch the chat box. You guys remember simple harmonic motion? You had a class with me when we talked about this. Kinematics, that's right. Simple harmonic motion is really just a wavelength that looks like the one that we see here. Oh, in physics, you also had it? Okay, in high school, excellent. And in calc and physics, yes. So we see it in a lot of different places. And here is another application of, and what we see is this wave that is going up and down at predictable heights, depths, and also frequencies. So as we look at this chart, this is going to be a wavelength that will represent over time what happens with that spring going up and down when we are at what we call free vibrations. Now, a free vibration is a system which will maintain its motion from restoring forces only, is said to be free vibration. So what is a restoring force? A restoring force is going to be one that, as we had stated earlier, something in nature that is going to allow it to go back to its equilibrium state. So for instance, it might be gravity, okay? But it's not going to be an external force that does that. It might be, as stated earlier, stiffness in either the system or the parts that are coming together, or in the material itself. So we're not doing anything to either create that vibration intentionally or to stop it, okay? So as we look here, this chart on the y-axis, this is going to be displacement. The middle right here is going to be that 0 equilibrium point, okay? If we are up on top or up on the bottom, which is going to be the peaks of our curves here, okay, that's going to be called the amplitude, okay? And the amplitude is going to be measured from our equilibrium state, or 0, in one direction up or in the other down. And because it's a simple harmonic motion, this peak amplitude will be the same on the top and on the bottom, okay, just by the behavior of this type of a wavelength. Now, as we measure from one point to the next, and they chose to do the peak of the amplitude from one hump, if you would, to the next, this is called the period. The period is going to be how much time it takes to go through a full cycle, okay, and back to that same point. So the x-axis here is going to be time, okay? So if we measure from one peak to the next, how much time does it take to go for one complete cycle, okay? And then how often it happens is going to then be what we call the frequency, okay? So as we go down here, some terms and relationships and some equations. Now, what we are going to do is develop our equation sheet through these next couple slides. So, so if you would like, I think this is a good time to get out a piece of paper. And what we are going to do is we're going to create our module 6, which is chapter 19 equations. Okay. All right. And we'll kind of take these in order of what we have here. So period first, the period is going to be the time required for a system to complete a full cycle of motion. So period is going to be called tau. It's the Greek letter tau, and it can be calculated by taking 2 pi divided by what we call the natural circular frequency, which is actually going to be our next term. So I'm going to go underneath. Okay. And we're going to start by showing, this is going to be period, okay? And this is going to be tau. Tau, which is capital T, Greek letter capital T. This is going to be equal to 2 pi divided by our natural circular frequency, okay? And that's omega with a sub n, that means natural, okay? Now, the units here are going to be seconds, okay? So tau is going to be the period, the amount of time it takes us to go through one cycle, okay? It's going to be our period. Natural circular frequency of the vibration, so that's that lowercase omega sub n, is the inherent rate for which the system oscillates or vibrates when disturbed, okay? So we're going to show this equation. This is going to be, what do we call that? A natural circular frequency. Yep. Okay. That's going to be our omega n. It's going to be equal to the square root of K over M. Now, the vibrations that we're going to be focusing on as our introduction here are going to be due to springs, okay? So K here is going to be our spring rate, okay? And spring rate is going to be in newtons per meter, okay? It's how much force to move that spring, a unit of measure, okay? I should really put newtons per meter or feet. I'm sorry, pounds per foot. Sorry. Pounds per foot. Getting it in the end here, pounds per foot. M is just simply going to be mass. And we know mass is kilograms, or it's going to be pounds times seconds squared divided by feet when we are in the standard terms. And then the units for our natural circular frequency is going to be radians per second. And those are going to be consistent for both units of measure. Okay. Now, spring rate can be calculated and is calculated using the force divided by deformation. Let's add that one because it's just good to know. I think we end up using it. So I'm going to say spring rate, and that's going to be K, okay? So K is equal to P over deformation, where P is equal to the spring force, and that's going to be in newtons or pounds, okay? And then deformation is going to be deformation. And that's going to be in meters or feet. Okay, those are kind of the standard that we report in. Okay. So spring rate, as shown up here, it's going to be newtons per meter or pounds per foot. And then that's how we calculate it. Force divided by the amount of distance that it moves that spring. Okay. All right. Couple more here. Then we've got just regular natural frequency. Natural frequency is going to be the number of cycles that we can get in a unit of time. Okay. So there's two ways that we can calculate frequency. Okay. So frequency is going to be equal to, there you are. It's going to be that natural circular frequency divided by 2 pi. Okay. Or it's also going to be equal to the reciprocal of the period. Okay, so and it truly is. Because if we go back up here to the period, it's 2 pi over the natural circular frequency, or it's the natural circular frequency divided by 2 pi. So depending on the information you have, if you already calculated the period, which is a very common thing to calculate in these problems, then you just need to take the reciprocal to get the frequency. Now, the units are going to be in hertz, okay? And a hertz is equal to a cycle per second, okay? Cycle per second. And that's for English and for metric, okay? Cycles per second. The next one here we have is amplitude. Amplitude is going to be that XM. We had seen it on our illustration. I'm just going to peek back up here. So here's our amplitude right here. So when we're from our equilibrium point, the XM is going to be a value as high as we can possibly go or as low as we can go. And that number is the same on any given cycle. Okay. So it's the maximum amount. And we're always concerned about the maximum amount because that's where the most damage can occur. So as you can imagine, the more severe vibration is of more concern. So we're always going to be designing for that worst case scenario. So what is the maximum displacement of the system from its position of equilibrium? So it's a distance. Now, when there is no external force that is acting to pull it or push it into a new position of XM, then our displacement of our spring is equal to that XM. Okay, just so that you know. So there's, I think, one problem where we see this happen. So I wanted to note that there. So actually, there's really not an equation for it. So I'm gonna go, we actually end up using amplitude. So I'm going to leave that there, but then we're going to define maximum velocity and maximum acceleration. And as you probably can imagine, that when we're in that vibration state, we're moving. So how fast are we moving and what is the rate at which we are moving at? And those are the velocities and the accelerations as we're vibrating. That's where we're going to use the X sub M, or that maximum distance. So I'm going to put that in here. So maximum velocity . And that's going to be Vm is equal to Xm. So that's going to be the maximum amplitude. And again, it really comes down to the distance for which it leaves equilibrium. Okay. Times our natural circular frequency. Okay. And as you can imagine, just like in, other places, we're going to have meters per second or feet per second, okay, as our units. And then maximum acceleration. It's going to be AM. It's going to be equal to our maximum amplitude again. And then we're going to multiply it by the natural circular frequency, but we're going to square that value, okay? And so just like other accelerations, we're going to be in meters per second or meters per second squared or feet per second squared. All right. All right, so those are kind of the core of the equations and concepts that we're going to be looking at in terms of the problems that you're going to be doing, and the sample problems we'll be doing are practice problems. Now, there's one other thing I want to go over, and that is going to be equivalent spring rate. Okay, equivalent spring rate. So spring rate, as we know, it's the amount of force that is needed to move a spring a unit of distance. So we know that K is that spring rate is equal to P, which is force, divided by the amount that it moves when we put that force on it. And this, again, K is active in the elastic limit of that spring. Okay, there is no permanent deformation occurring, and it's completely predictable, Hooke's law. Now, there are two arrangements of springs that we can have on a body. So when we have multiple springs, this is when we need to determine what is the equivalent spring constant, okay, or the spring rate. So if we have just one spring that we're dealing with, which I think has been the problems that we've seen up until this point, we're given the K and we can use it in our equations. But notice here that we have a situation where we have two springs that are holding up this block, and we have two different arrangements. Now, if the two springs are side by side, this is called springs in parallel. Okay, so they're parallel to one another, and we are going to determine the equivalent spring rate, K. It's going to be equal to simply adding together each one of the spring rates. So in the case of the one over on the right-hand side, we would simply take 4 kilonewtons per meter plus 6 kilonewtons per meter, and we get an equivalent spring rate of 10 kilonewtons per meter. And that's this arrangement right here. That's the spring rate, the effective spring rate, or equivalent. If we look on the right, we have now these springs kind of chained together one to the next, and that's in series. In series, the calculation for the equivalent spring rate is going to be 1 over K is equal to, and then we're going to take the individual spring rates 1 over for each one of them to get the value. So using those same spring rates here, we would simply take 1 over K is going to be equal to 1/4 plus 1/6 in terms of kilonewtons per meter. And then we would get the reciprocal, and we would find that that's going to be 2.4 kilonewtons per meter. Okay. So we want to write down these two equations for spring rates. So equivalent spring rate. Okay. So for parallel, we're going to have K is equal to K1 plus K2 plus, and then I'm just going to put, however many springs in parallel are holding it up. Sometimes there can be 3, okay, or 4. So however many there are, we simply add those together, and that's going to equal the equivalent spring rate in parallel. And then in series, again, chain together one to the next to the next. This is going to be 1 over that equivalent spring rate. It's going to be equal to 1 over K1 plus 1 over K2 plus ... however many are chained together. All right, any questions so far? So that, I believe, is all we need on our equation sheet. Okay, so now we are set up nicely to do our first sample problem. Okay, so I'm going to go back, and we are going to go to our next slide. So our first sample problem this evening is going to be sample problem 19.1. You will find this on page 1358 in your book. I'm going to kind of stick here because this is a nice illustration rather than trying to go underneath. Sometimes it gets a little blurry with that shiny paper. So we've got a 50 kilogram block. It moves between the vertical guides as shown. The block is pulled 40 millimeters down from its equilibrium position and released. So right now, this is equilibrium. And what it says here is we're going to pull it down 40 millimeters. And as you can imagine, now that's creating some stretch in that spring. So if we let go, it's going to now start kind of bouncing around and creating a vibration, trying to get back to its equilibrium spot. So for each one of the spring arrangements, the parallel and then the series, we want to determine the period of that vibration that occurs when we pull it down 40 millimeters, and then the maximum velocity and the maximum acceleration of that block. Okay, and we're going to use those equations that we just found, or we just put on our equation sheet. So this is going to be sample problem 19.1. Okay. All right. So let's first write down what we know. So we know that the mass of that block is 50 kilograms. We also know the spring rate of our spring number 1 is 4 kilonewtons per meter. Now, if we look back at our equation sheet, we need our forces to be in newtons, okay? And we need our distances to be in meters. So in this case for K1, I'm going to write 4,000 newtons per meter. Because again, I don't want to put in kilonewtons, and then if I inadvertently, kind of forget, then my other units may not come out appropriately. So make sure that you put these in their standard units. And then K2 then is going to be 6,000 newtons per meter. Okay. The distance that we're pulling it, past its equilibrium position is that XM, maximum distance. And this is going to be 0.04 meters, because again, it gave it to us in millimeters, 40 millimeters, but we're going to use the meter equivalent. We need to find, we need to find the period, which is tau. Okay. We need to find the max velocity, which is Vm. And then we need to find the max acceleration, which is going to be AM. Okay. All right. Now, as we look here, since we need to find these 3 quantities, what I'm going to do is, again, the sample problems and such, they tend to just jump in and start solving, but it's kind of like, well, why are you starting where you are at? So let's first look at the equation to solve each one of those quantities. So we've got our period, it's going to be equal to 2 pi over that natural circular frequency, okay? Velocity max is going to be XM, or that maximum distance, times the natural circular frequency. And then acceleration max is going to be equal to that maximum distance again, times, or the amplitude. It's going to be times the natural circular frequency squared. So as you see here, we're going to use that natural circular frequency in each one of the equations. So I guess it makes sense to calculate that first and then use it in each place. So part A here, we're going to find our period. But before we can, we need to calculate first our circular natural frequency. Now the natural circular frequency is this quantity, and it's going to be the square root of K divided by M, okay? So we know that to be the square root of K divided by M. Now, this is one value of K, which is going to be the equivalent spring rate, and we're going to look at the parallel first. It's going to be the equivalent spring rate of these 2 springs. So we've got K1 equal to 4,000 newtons per meter and K2 equal to 6,000 newtons per meter. Parallel arrangement. So if we go back to the bottom of our equation sheet, the parallel arrangement, the equivalent spring rate is going to be just simply adding those together. Okay. So that means that my K is going to be equal to K1 plus K2. So I'm going to have 4,000 newtons per meter plus 6,000 newtons per meter. So my K here is going to be 10,000 newtons per meter. Okay. I'm going to plug that in right there. Then I'm going to divide it by the mass. The mass is 50 kilograms, okay? So that means that I'm going to have 10,000. And I'm going to put newtons per meter, okay? I want to show you how the units come out, okay? You don't have to put the units in for your problems, but I can't imagine that anybody isn't wondering, like, do these really come out the way they're supposed to? So a newton per meter, a newton expanded is a kilogram times meters per second squared. And then that's going to be divided by meters. Okay, so the top is a newton per meter divided by 50 kilograms. Okay, and then we're going to take the square root, right? So as we look here, if we look first between these two, I've got meters, I can cancel out top to bottom. And then I've got kilograms, I can cancel out top to bottom. What's left over? Seconds squared, okay, in the denominator of the denominator. So it's multiplied on top. So that means that I'm going to take the square root of seconds squared, and it's going to be nothing over seconds, okay, when I take the square root. So the units then are going to be, this will be my number, radians per second. Okay. So let's take 10,000 divided by 50 and take the square root. What do we get for our number?
I got 14.14.
Yeah, 14.14. That sounds correct. Thank you. So I'm going to put my little cloud around this because we're going to use this then for all three of these quantities. Okay. All right. So tau then is equal to 2 pi divided by our circular natural frequency. So 2 pi divided by 14.14. Tau is equal to, tell me what you got. 0.444. Yep, that's what I got too, James. Thank you. Now, units. We are radians per second in the denominator. So that means that in the denominator multiplies on top. So this is going to be seconds. And this is a box because that's our first quantity that we need to calculate. So that is the period. Tau is equal to 0.444 seconds. If we go back to our illustration here, that is this value right here. So to do 1 second, so like an up and a down, if you would, for our block as it's attached to those springs, it's going to take 0.444 seconds to go up and down, up and down, up and down. Okay, that's what that value means. Okay. Part B, we want to know what the maximum velocity is. Okay, so max velocity, and that's going to be VM. Okay, maximum velocity. So maximum velocity, if we go back to our equation sheet, is going to be our max amplitude, or that xm distance, times the natural circular frequency. Okay, so VM is going to be equal to xm times omega n. So this is going to be 0.04. Make sure that you put this in meters. If you do the 40, that's in millimeters. That's incorrect. Okay, multiplied by our natural circular frequency of 14.14. And I'm just going to put the units in here just because I think it's important for you to see it. You don't have to add them, but why wouldn't you want to? And then what do we get for our maximum velocity? Yep, you should get 0.5656. Now, I want to remind you guys, when you're handing in, please do not just put a box around your number with the units. Label it for me to let me know what it is that you're solving for. I see a lot of this, okay? So that's a nice number with units, and I know what it is when I look at it, but make sure that you label it so that when you look back, especially on something like a final exam, you know what it was that you solved for. Okay, and then part C, are you already that far ahead, Josh? Oh, you are so good. We'll get there. Now we're going to do our max acceleration. Okay, that's going to be AM. And our max acceleration from our sheet is going to be the maximum amplitude times the natural circular frequency squared. Okay, so AM is equal to XM times omega n squared. So again, it's going to be the 0.04 times the 14.14 squared. Don't forget to square that. And you should get 8 meters per second squared is equal to the maximum acceleration. And now this is when we get to the highest and lowest points on our curve. So if we go back here, that is going to be the velocity at the end of that maximum amplitude, because that's the X value that we used. Okay. And then it's going to be the acceleration at that same point and then opposite direction. So depending on which side you're on, you're either going, you know, up or down, up or down. So, so direction wise, if you look in the book, they show a direction on both of these kind of going up and down. You don't have to, you know, put that on there, but that's what that means, depending on which side of that simple harmonic curve that you're on. Questions on this first part? Okay. So we're going to do that very same problem, but the second way that we're going to look at this, so it's going to be like, if you would, part B is going to be now looking at it in series, okay? In series. And really the only thing that changes here, but it does make a significant change, is that our equivalent K factor is going to change, but then we are going to proceed and then finish up the calculations the same way. So I am going to turn my paper over. And now this is going to be for the series springs. Okay. So I am going to calculate first my K value. So I know that I'm going to have my equivalent K. So just my regular K, it's going to be equal to, so 1 over K is going to be equal to 1 over K1 plus 1 over K2, which is going to be equal to 1 over 4,000 plus 1 over 6,000. So our K, what do you come up with? Going like uphill there. What do you get for K? Don't forget to take the reciprocal at the end for the equivalent value. It's not 10,000 this time. Yes, 2,400. Yes, 2,400 newtons per meter. Okay, so I'll put a little cloud around that. Not a final answer, but we will need it. Now, as we had done for the last one, we are going to calculate those 3 values for each. So we need our tau, our period, our maximum velocity, and our maximum acceleration. So we're going to go ahead. I'm going to do the tau first, or the period. Okay. So A, going to be tau. You can put the N or not. And then it's going to be 2 pi divided by our natural circular frequency. So we need to calculate that, don't we? I didn't do that one yet. So let me do my Wn. It's going to be equal to the square root of the K value divided by the mass. So I'm going to use my K value up here. 2,400 divided by 50. I'm not going to do the units again this time because we already went through that. So my natural circular frequency, what do we get for this number? should get 6.93 radians per second. And that's what we're going to use up there. Okay. So tau is going to be equal to 2 pi divided by 6.93. So tau, our period, should come out to be, and that's the one you had earlier, Josh, 0.907 seconds. And again, that's how much time it takes to go from the one peak to the next, the next. That's the time in between. Part B is going to be the maximum velocity. So we can take Vm is equal to Xm times our natural circular frequency. So this is going to be 0.04 again, the meters, times 6.93 radians per second. So our maximum velocity be 0.277. Then our last one is going to be our maximum acceleration. And we're going to square the natural circular frequency this time. Okay. So you should get maximum acceleration equal to 1.921 meters per second squared. So those are the three parts for both the series and the parallel. Now, things that you notice, okay? First of all, as we look at the K factor, the K factor for the parallel was 10,000 newtons per meter. And the K factor for the series was 2,400. What does that tell you about? I mean, what would you say about the difference in the arrangement of those two springs? Same springs, just arranged differently.
Series springs are not as efficient.
Oh, I don't know. What do you mean by efficient?
Well, they don't have as much of a K factor as parallel ones.
Well, but what does that mean to us? K factor, the higher the K factor, what is the characteristic of the spring? Stiffer,
higher the K factor, the stronger it is.
What was that?
Higher the K factor, the stronger the spring is.
I wouldn't say that. Be careful. Look at your units here. Newtons per meter. Which one is easier to move? 2,400 newtons per meter or 10,000 newtons per meter? Which one is stiffer? Maybe I'll ask it that way. Is it the one in parallel? Is it the 10,000 or is it the series?
10,000 are stiffer.
Which one's stiffer? Josh says the parallel. You indeed are correct because it takes, if this value is newtons per meter, so to move 1 meter, I need 2,400 pounds. To move 1 meter here, I need 10,000 pounds. Okay, so very different applications, very different amount of force to move it. So I don't like to say efficient, but one is going to be much stiffer than the other. And when it's much stiffer, it takes more force to move the same amount of distance. Okay, then you can start looking at the vibration itself. In this case, this is a stiffer spring, right? The time for one period is 0.444. Okay. And if we look over here, a period, and this goes from peak to peak, is 0.9. It's like double, right? So when we look at, go back over here, when we look at a more stiff spring, this is closer together. It's like half the distance. So on a stiff spring, it's going the same distance up and down. So like it's high and the lows, the amplitude is the same, but how often it's happening is much more frequent. It's double. Okay, so a stiffer spring is going to vibrate faster than a less stiff spring, or in this case, a spring that is in series. Does that make sense to everybody? Okay. What the other thing that we see with the velocities, the velocity here is 0.565, and the acceleration is 8. We look on the other side where we've got our series, half the velocity and like a fourth of the acceleration. Now, when we start looking at things like acceleration and vibrations and things moving, which one would we rather deal with? An acceleration of 8 or an acceleration of 2? The 2. Yeah, absolutely. Lower accelerations are easier to stop. They're easier to get going. They're going to calm down quicker. Okay. So, depending on the requirements of the system, I'm not saying one of these arrangements is better than the other, but if you're going to have, a more to deal with, it's going to be on the first one, because these accelerations are getting pretty high to try to, control. So that's that. So just kind of, like I said, not really one is better than the other, but the behavior is going to be different. Okay. So that's our first sample problem. I am going to stop the recording here and we'll go to our next one after this.